Can't really sit all the way back in this chair because got some ice here. Well, welcome to Theoretical Physics. We're going to look at a course here that is a little different than the one I taught earlier. This one has the prerequisites of Calc 1 and Calc 2 and no physics. So the first class we're going to review or introduce, would be a better way of saying it for the first time, some physics concepts in case you haven't had physics before. So this is going to be like cool physics from the intro physics course that's going to get us started. That's the intro class. The course is designed to have a lot of physics introduced in a novel way, perhaps a little different than the way you see it encountered in your regular physics courses. The emphasis is on theoretical understanding of the equations in an elegant fashion. And that's subjective to a large extent. Not everyone will agree with my way of looking at things, and that's okay. I encourage you to have your own way of looking at things. It's very important to see physics in your own way. But at least by giving you my way, you have an example of how you can integrate and put physics together. And then the second part of the course will have a lot of mathematical methods that are used in graduate school in engineering, physics, astronomy, astrophysics, and they're very, very powerful. And they're used so often in diverse fields of interest. So I hope you like that. That's the mathematical physics. In fact, some people refer to this course as mathematical physics. They teach it that way in many, many schools where they do the methods of physics and call it mathematical physics or math physics. So I hope you enjoy the class. And some of our lectures, presentations are from the spring, since we do have some lectures that we did when we started going online in 2020. So there'll be a little mixture there. Okay, and all the notes you'll find at drphys.com, www.drphys.com, all the notes and materials, homework assignments and solutions posted when after they're collected and graded. Okay, good luck. Hope you enjoy the class. Intro Physics. And we'll start with Intro 1, linear acceleration. Let's consider being in a car where the velocity starts out at some speed and you're going to put the accelerator pedal on more to gain speed. So now our units for velocity, and we do this little bracket for the units, for the dimensions, meters per second, could be miles per hour. That's how you write per with the line, because if you were to consider, for example, going 150 miles in 3 hours, you would have 50 miles per hour. And the units here for acceleration would be meters per second. So we put a little second squared there. You could think of it also as miles per hour per second, where you're going 50 miles per hour, then in 1 second you're going 51, and then in the next second 52. So the acceleration would be 1 mile per hour per second. Now we can graph this. Where we have the time and the velocity. And we start out at some initial velocity, and this is a straight line. Now I will tend to use the variable twice here. I mean, this is the t-axis, but then this distance along this axis represents the time, t, some arbitrary amount of time. And if you look at this graph, you can see that you have here, this height is v naught, corresponding to v naught. And then this extra piece here is a times t. That's how you can graphically see what these things mean. Or the equation like y equals mx plus b, where then the intercept is the v naught and the slope here is the a. Now, a nice thing about this is that if you look at where x is, where your distance, so we're looking here, say x and t, and say we can start off at some x naught, some initial place when t is equal to 0. Then what happens here is that you basically are taking the area under this graph. Now you could see that easily for the case that the velocity is equal to a constant, v naught, then you would have just the v naught and no change. And this is the time. But see, if this is your speed, like if this were, for example, be 50 miles per hour, and say this distance here happened to be 3 hours, then you would be going by your formula, velocity times time. It'd be 50 miles per hour times 3 hours is 150 miles. But see, that's taking the 50 and the 3 and multiplying. That's the area under the graph. Now, when you go from a graph to the area under the graph, that's called integral calculus. So by going to the left here, it's finding the area of this graph. So the area of this graph would have two parts. It had the v naught t, and then it would have the area of the triangle, which would be 1/2 the altitude times the base. So that would be 1/2 at times t. So it's 1/2 at squared. So the general formula over here would be some initial position plus v naught t plus 1/2 at squared. And the graph that goes with this formula goes with the graph. We can write it underneath it like that. And this is an equation of a parabola, so it would, do something, go something like that. Now, if you go the other way, for example, if the velocity is a constant, then the x is the velocity times the time. So here, if you started out, say, at 0, let's just say you start out at 0, then you would just have, this is the slope. So the slope is constant, say. So going from left to right is finding the slope information, and that's differential calculus. So we're getting a lot of cool stuff here. So to go this way, and you might remember from your calculus, the derivative of a constant is 0. The derivative of this one would be v naught. And the derivative here of t squared is 2t, and it would cancel, and you would get this. So that's a differential calculus. And see, physics helps us understand calculus in a nice way. And if you were to plot the third thing here, the acceleration is a constant. So the slope here is a constant. So you could actually have these three graphs: position, the velocity or speed, and then the acceleration. And to go this way, this is integral calculus. And that's amazing that taking the area is like the flip of doing the slope. And notice when you take the area going to the left, you get a constant of integration. That's what that V naught is. And then here, another constant of integration. So you can think of like if you started here and integrated, you would get this equation. Then integrate again, you would get that equation. But I'm more fond of just doing a simpler case where you have, say, the parabola. For example, if you have the parabola y is equal to x squared, then here, if this is, say, your x, and this is your x plus delta x, I kind of like to just do x plus delta x squared for the big one, then minus the x squared, and divide by here delta x. I think this is cool. This gets the essential idea of the quadratic. Then you have x squared plus 2x delta x plus delta x quantity squared minus x squared over delta x. These go out, and then you get 2x plus a delta x. And then if you're looking at your limit, as delta x goes to 0, this is going to be 2x. So you're basically showing that the slope of a x squared is 2x, or a t squared is a 2t. So here is a nice little picture from our book that shows 3 cases: constant position, and the 3 graphs where you don't change your position. Here's a constant velocity, and then here's the one that we did. And differential calculus gives you slopes going to the right, and integral calculus gives you areas going to the left. And here I have some formal derivative and integral showing you the same thing we talked about. So the acceleration near the Earth, if you look at the Earth and you have a ball and you drop it, the acceleration is due to gravity. We often call that little g. And that's going to be equal to, here, 9.8 meters per second squared. Also 32 feet per second squared. That means like after 1 second, if you start at rest, you're going 32 feet per second, or you're going 9.8 meters per second. Then in like 2 seconds, you're going to be going like double that, because you remember V is acceleration times time. If you start out from 0, then that's like the formula simplifies. Okay, and a picture in the book of a Chimney Rock, not too far from where I live, showing height, and a little table showing that in a half a second you would fall a meter 1.2 meters. Now this is neglecting the air resistance. Then in 1 second you would go 0.9, because you remember your distance is 1/2 AT squared. So when you put the A in as 9.8, 1/2 of that's 4.9. So the T squared is working on the 4.9. So that's neat. And now we go to acceleration that's due to circular motion. So here, this would be intro to uniform circular motion. Now there are many, many ways to derive the famous formula that we learn in intro physics for the acceleration, but I'm going to show you one that I'm very fond of. Here, if we look at, say, the radius, say, of a circle, and here something's moving in a circle like this, and if it were going in a straight line, say, it would be up here, but it's going to wind up down there. So it's like it fell a distance h. Now the velocity times time would technically be the part of the arc, because if you're going velocity, so many meters per second, and you go for a certain time, this is where you're actually going. But when your time frame is getting very, very small, then you're going to find that this arc is going to agree with this distance here, pretty much. There, it's going to approach it. So now we can do a nice little equation with the right triangle here, that the hypotenuse, which is r plus the h, that's equal to, if we square it, that's going to be equal to r squared, this one, plus this other leg, which I'm going to take to be v squared t squared. In other words, this other leg is, this one here is vt, and we're squaring it. So this would be r squared plus 2rh plus h squared is going to equal this other side. But then you can see that this is going to cancel, and you're going to have 2rh plus h squared is equal to v squared t squared. Okay, now this h is going to be very small, and compared to r, like you're going to throw it away. So in other words, here's a big number, r times h, and here's the two little ones squared. So that means we're going to kick this one and have 2rh is v squared over t squared. And then if we bring the v squared over here, or let's say the h, we want the h over there on the left. So then you have the v squared, you want to have the h by itself. So this is then 2r is underneath there times the t squared. But remember our formula, 1/2 at squared, which means that the a is equal to v squared over r. So this is acceleration due to changing direction, not changing the speed. Like the speed stays the same. You can think of the velocity as a vector where you put a little arrow over it, and you can change the magnitude, the v, like going 50 miles per hour to like 51 miles per hour, or you can keep the velocity the same and like go in a circle, and you are accelerating. You are changing the velocity. Say, so like if you were going like up here, you were going like that, and then a little bit later you're going, say, this way, then like you change, you came down. See, that's the idea. And if you look at the moon, for example, for the moon, if you put in the r, there's 384,000 kilometers, and you put in for the velocity, you have the circumference of the moon's orbit, 2 pi r over the period. Now you would use here the period with respect to the fixed stars, and that's 27.3 days. And if you multiply all of that out, as I do in the book here for you, you get an acceleration right here. 2.72 times 10 to the minus 3 meters per second squared. So this is finding, you find the t first, and then after you find the t, you find the velocity. That's the next step. And then the last step is you take the velocity squared divided by the r, and you have all the stuff here. So like that's the answer. So the moon, say, is falling to the earth. You can think of it that way. So we move to intro 3, and that would be Newton's second law, as we're reviewing, or we're covering for the first time basic physics, so you don't need to have your intro course to take my theoretical physics class. When you apply a force on a mass, you get acceleration, and this is the famous result. This is like how much stuff you have, and if you have lots of stuff, then the change of motion, the acceleration, is not as great. If you're very, very light in mass, then the change in acceleration would be more given the constant f. And since we have direction with force and acceleration, we put a little arrow on there to represent the vector. And your acceleration can be thought of as your derivative of the velocity vector with respect to time. That's the general formula. Therefore, the force is m times dv dt, but you could have a situation like a rocket where when the rocket is moving this way, it's throwing out mass. So the mass is not a constant. The mass of the rocket's going to change. So in that case, we look at a more general result where we have d dt, we put the mass inside with the v, and then we see that this is a natural appearance of another parameter, which we will call p, which is the momentum. So a truck has momentum if it has more mass, has more momentum, and if it has more speed. And the scalar result, scalar just means just the magnitude, not the direction. You could write it this way, and that includes the direction, a little vector sign. So Newton's second law can be written as the change in momentum with respect to time. I'm using a lowercase p there for momentum. That's what they usually do. Use a little p, and capital P is often used for pressure, and they use the little p for the momentum. So if you want to analyze the dimensions here, now they do name this after Newton, and when they say newtons, they don't capitalize like 5 newtons, like that's the value of a force. So the force units are newtons, but also that's the force is equal to ma. So we take the units of the mass and the units times the a. This is in kilograms, and then this is in meters per second squared. So therefore you can write down a newton. Now they do capitalize it when they make the abbreviation, is equal to kilogram times meter per second squared. But this means that meter per second squared is equal to Newton over a kilogram. So you might have recalled that the gravity is 9.8 meters per second squared. You can also write that as 9.8 newtons per kilogram. So that's how much force is pulling down, see, on you, because the F is equal to ma, and that would be mg, and this would be pulling you down. So if you're on the ground on a scale, this would be like your weight. This would be your weight. So it's kind of neat to see how all these units are related. Okay, now we go on to Intro 4, and that's the universal law of gravitation. And here we go. Nice little picture from the book. Unification, because what Newton is doing is taking terrestrial motion, which would be your gravity near the Earth, like the d is 1/2 at squared, and then he's going to relate that to the celestial motion in the heavens, which is your circular motion, where we saw there was acceleration. So here, before Newton came along, they thought there were 2 different laws. Actually, before Galileo and before Kepler, they thought that they didn't know what the laws were, but they just thought that the heavens had the circular perfection, and the Earth, like things fall straight down, like different kinds of motion. Then Galileo started explaining that in terms of the pull down, like the d is 1/2 at squared idea. And then with Mars's orbit and then studying other orbits, Kepler found that the time it takes a planet to go around the sun, if you square it, and instead of equal to r cubed, now they would have different constants in there depending on the units, but if you take the r to be 1 astronomical unit is how far the Earth is from the sun, and t is equal to 1 year, then this would work. 1 times 1 is 1 times 1 times 1. And then the brilliant connection here that Newton made, I can show you in a nice little way, the ratio. We have found that the ratio of the moon's acceleration, well, we know that, 2.72 times 10 to the minus 3 meters per second squared, already figured out. And this is 9.8 meters per second squared. So by taking this ratio, you get 1 over 3,600. But since the moon, if you want to go to the moon, all right, the moon distance is 60 times the radius of the Earth. So this is really the moon orbit. So the radius of the moon orbit is 60 times. So if you have the Earth here and you go up there to find the moon, so if you're looking at 60 times this way, but then the acceleration is like 1 over 3,600, 60 squared is 3,600. So this is inverse square law. So you can see the connection here from our two basic definitions of the acceleration, linear versus the circular. So that brings us to this cool little picture where we have the Newton's law of gravitation, where you take two masses, get the distance between their centers, and it's inverse square, 1 over r squared. Big M is the mass of the big one, little m is the mass of the small one, and g is gravitational constant. So that would be Newton's law of gravity. So big G, mm over r squared, where the g is 6.67 times 10 to the minus 11 Newton meters squared over kilogram squared. Now, how do I know I need to have those units? Well, I know that this has to be newtons. That if I have the force, the dimensions have to be newtons. And that means here that I got dimensions of G and dimensions of M, and dimensions of R squared. That's going to be dimensions of G, and this is kilograms, that's kilogram squared. This is meters squared. So if I want what G is, I gotta then look at over here. I have newtons times the meters squared and divide by the kilogram squared, which is what I have here. It's always good to know your units. There's a fun paper I wrote many, many years ago on Kepler's third law without a calculator. And before I show you that, though, let me show you this beautiful derivation of Kepler's third law. So you have here the force on a planet. This would be the sun and the planet here in a distance between the sun and the planet. So you can just think of this as a planet in orbit around the sun. That's equal to force, and that's equal to ma. And the acceleration here is going to be v squared over r, because it's a circular, we're going to assume circular orbit. A lot of the planets go in orbits that are pretty close to circles anyway. So here the m's cancel, and you have big G, big M over r squared is going to be v squared over r. But remember, your v is 2 pi r, your circumference over the period. So we got that, and then there's the 1 over r. So when you do this, you get 4 pi squared r squared t squared 1 over r. And here, that's 4 pi squared. One of the r's go away, over t squared. And then if you look at these two here, you can see that if you bring the r on the left-hand side, you're going to get gm over r cubed. And then on the right-hand side is 4 pi squared over t squared. And now if you bring the r cubed to one side, you would have then r cubed is equal to gm over the 4 pi squared t squared. So this is your Kepler's third law, that r cubed and t squared, and you could write it either way. You could have, for example, t squared 4 pi squared over gm r cubed, that the square of the orbit is equal to the cube of the distance. Circular orbits here, a little simplifying, but still it actually does apply to when you have an ellipse. You would take the average here of these two and use the semi-major axis. That's a little more advanced. You would study that in mechanics course. When I taught astronomy, I had some fun with teaching students that are not majors in science, doing Kepler's law, talking about the planets, and we're able to do a lot of cool estimates. First, let me point out Titius-Bode, the Titius-Bode law, also known as Bodes Law. It gives you the distances to the planets from the sun with remarkable accuracy, and it's a number sequence. No one has ever derived this formula from first principles, so we believe it's an accident. You start with 0, you put down 3, you double, get 6, double, 12, double, 24, double, 48, double, 96, and we'll do one more here. When they came up with this law, they knew about Saturn, and we're going to talk about that Saturn result. But first, the rule. You add 4. Then you divide by 10. This is Mercury. This is Venus. These are astronomical units from the sun. This is Earth. Mars is about 1.5. This is asteroid belt. Has an average around 2.8. This is Jupiter. Saturn. Saturn's more like 9.5. And then this would be a planet they predicted the next one would be there. Uranus, or Uranus. And these are remarkably close. So using Kepler's law, say T squared is R cubed, where we have astronomical units and we have years, Earth, you would have 1 year, and the distance from the sun, 1 AU. That would be the average of the closest and farthest point, also called the semi-major axis. It's pretty close to a circle. And then here you can see that 1 times 1 for T squared is 1 times 1 times 1 for the R cubed. Jupiter is next. Let's do Jupiter. And if we take Jupiter, it's about 5 AU, then R times R is 25, and then R times R times R is 125, which is approximately 121. So what number times itself is 121? T would be 11 years. Jupiter is actually 5.2, is 5.2, so that pushes it up a little bit. It's something like 11.9 years, but this is pretty impressive estimate that we're making here. And if we look at Saturn, where R will take it to be at 10, then R cubed is 1,000, which is roughly 900, and then T squared being 900, T would be 30 years, and for Saturn it's something like 29 point something. It's like it's close to 29, so it's very impressive to get these results. Let me show you the power of this Kepler's law to estimate how long it would take to send a spacecraft to Jupiter. Say we have the sun here, and we have the Earth going around the sun, and this is 1 AU, but then if you go 1, 2, 3, like 4 or 5, you're at the orbit of Jupiter. And here we go with the kick here, like we send the rocket off to get the momentum here. And then Jupiter might be there, and then it's going to meet us up here. So this would be something like this, which is like elliptical, part of the elliptical orbit, where you have 5 AU and 1 AU, so the average is 3 AU. And if you take r cubed, you get 27, and then if you take the square, 27 is very close to 25, which means t is 5 years, and to go half the orbit would be, for the flight time, that would be 2.5 years. And a spacecraft left like in 1977 and got to Jupiter in 1979. This is rather remarkable that you could, in this short time frame calculation, estimate how long it would take to send a spacecraft to Jupiter. Okay, intro 5 is going to be work and kinetic energy. So now we're going to play a little game. We're going to take, for example, the definition of work. Now, work is, this is work. This is going to be your force times your distance. And I like to think of this as having a warehouse, and we're trying to load some trucks over here, and we have things on rollers. We got refrigerators, we got washing machines, and folks need to push these things different distances, to get there. And if you want to pay people to load up your van here at some big semi, you would say, well, look, if you're pushing something that's with more force, I should pay you more. And if you're going to push more distance, I should pay you more. So this makes sense. Force times the distance is the work. And then say, for example, someone should push up against a wall. Like, let's say someone's up against the wall pushing. Then since D is equal to 0, you get no pay. Like, you're wasting. You're wasting. Or suppose you're walking around like a zombie where the force is equal to 0, then force times distance 0. Or say you're laying down on the job, then F is equal to 0, D is equal to 0, it's still 0. So if you don't push the things to the van or to the semi, and you don't have a force, then you're going to get no money for your work. So that's your work. It's force times the distance. And if you apply the force at a different angle, this means in the direction. Okay, so then if you have a function, force that's varying with respect to x, then it's time to do an integral. At a little bit of distance, integrate this out. So if we do this, and we use F equals ma, then this is ma, and this is dx. Then this is m. What is a? It's dv dt. And this is dx. And now watch this trick. A little chain rule. M times dv dx, and then dx dt. So we still have the dv dt. And now watch this trick. We're going to move over, put the dx dt first, the dv dx second, and then replace this with dv, and then replace this with v. So now I have an integral mv dv, right? And that's going to be 1/2 mv squared. That is so cool. So let's go over that again, a little bit tricky stuff with calculus here. So F is equal to ma, and A is dv dt, and then dv dt is dv dx, dx dt, chain rule. Then we're going to move the dx dt first, just swap the order, put that first, and then we're going to notice that dv dx dx, another like chain rule idea, can be replaced by dv. So then you have a change of variables. So you would integrate here, say v is equal to 0 to v. Say I'm starting from rest. then I would have here 0 to v, and that would get me, this integral is m v squared over 2, and 0 to v gets me 1/2 mv squared. So that's called energy. In other words, I do some work, and then in outer space where there's no friction, I let go, and then that velocity I now have is the result of me doing the work, see, doing the work. So that's called kinetic energy. And sometimes you see Ke like this, 1/2 mv squared. Very nice. Okay, we go on. We go on here and apply in a little more generality. Then you would say, suppose I integrated from v1 to v2. Well, that's okay. You would then have 1/2 mv2 squared minus 1/2 mv1 squared. You would just have, you would replace the 0 with v1 and this with v2. And so this means if the mass was already moving, it had some kinetic energy, this one, and then you applied the force, then you would have put in additional energy, the difference there. So now we're looking at Intro 6, the concept of potential energy. And for potential energy, what we're going to do is, first of all, look at gravity near Earth. So we're going to drop a rock. We're going to drop a rock. So if we drop a rock, a mass m, we drop a rock, then the force is going to be here, and I'm going to use here a minus mg because I want to be careful with the signs. I'm going to call up is your positive z-axis. So up is positive. So that means this would be negative, mg pulling me down. And then when I integrate from a big Z to a little z, there'll be another minus sign coming in. So here, I'm going to write down f dz is then minus mg, and then there's a dz. This is a constant. So integrate here from h to 0. So this is h, and then I'm going to wind up with 0. It's my final destination. So this is minus, well, this is actually a plus mg, and now dz. I can switch this integration. And some people like to just do it like this and forget all this other stuff. They like to say, look, just pick the mass up. If you pick the mass up, you're going to go from the ground, pick it up to h, and then when you get that, you'll have potential energy. Then let it go, you'll get your kinetics. So if you prefer that way, that's fine. You just start with this and don't worry about any of this stuff. Say just pick up the rock, and that's going to get you mgh. And that's going to then be your potential energy. That's going to turn into kinetic when you drop it. All right. So when you do that, you'll get your kinetic energy 1/2 mv squared. And notice that the m's cancel out here. Probably shouldn't do that, because if I do that, I should do this. All right. And then I would have v is the square root of 2gh by just putting the 2 over there and taking the square root. But you know what? That's exactly what we expected from our first discussion. Remember, d is 1/2 at squared. And your acceleration here is constant, which you could call it, g if you want. So you have d is 1/2 gt squared. So we had that from before. So that means t is 2, and this is h, 2h over g, that's t squared, 2h over g, and that means t is the square root of 2h over g. But if you were to look at your velocity, it's your acceleration times time. So what is g times the square root of 2h over g, like that? Then you get the square root of 2gh. You get what we had there. This is sort of a shortcut. This is called conservation of energy. So since the potential energy, this is mgh, the work, we're going to call that U. That's potential energy that if you have a rock up there and drop it, then down at the bottom, you'll have no potential energy because you're at the ground, 0, and you'll have all kinetic energy. So what they do is they'll write down, for example, kinetic energy plus potential energy, say at 0.1, is equal to the kinetic energy plus potential energy 0.2. So here at the top you had 0, and then here you had mgh, and then here you have 1/2 mv squared and no potential. So in general, though, you could have a little bit of both. So the total energy would be 1/2 mv squared plus mgh. So this is a conservation of energy. Like that would be the same at all the points. So that's kind of cool to see that. So in other words, 1/2 mv at 0.1 squared plus mgh1 is 1/2 mv2 squared plus mgh2. And like this is a constant. All right. So potential energy, mgh. Now for B, we have the gravity far from Earth. And if we're far from Earth, then we're going to do the integral of the force with dr, and I'm going to here go ahead and drop it from infinity. So I'm going to drop down from infinity to some r, say some infinity to r, to find out what's going on here. So we're going to come down here, we're going to go from infinity to r, and this is then gm has a minus sign. Pulling back, so force pulling back like this. Okay, r goes out this way, so that'd be negative. And that would be here. What I can do is I can flip the order of integration and go from r to infinity and have gm m over r squared dr like that. And if I do that, I will then get minus gm m over r doing the integral and go from r to infinity. And this will be gm m over r. And that's going to be translated to the kinetic energy, 1/2 mv squared, see? Because that's like doing the work to get me going, I drop from rest. So we start out at rest and let go. All right, then we're going to get this. If you were to do the integral, say, and go from some r1 to r2, just set this up like this, all right, in general. Then here, I would have, this would integrate to a plus with the r, r1, r2. If you take the derivative, you get a minus sign, come down, and be r squared. So this is then going to be gm m over r2 minus gm m over r1. And that's going to be the final kinetic energy, minus the initial kinetic energy, if I start out in general. And then I can collect everything on one side, like all the ones. I would have a 1/2 mv1 squared. Okay, so collecting these, I'm going to put this one on the other side. So we would have this. And then this one here, if I subtract the other one, I get this. Let's just make sure we did this right. Might be helpful to write this side by side. So let me just write this top one side by side. Just bring this one over here. So I want to have the ones on one side of the equation. So I need to add this to the other side. So the v will have a plus sign, but then there's a minus sign with the 1r. And then here, by bringing this one on this side, it comes on with a minus sign. So basically what we're saying here is that what's the constant is the 1/2 mv squared minus gmm over r. So that means your potential energy when you're far from, say, the body is given by this formula. There it is. Notice that the reference here is at infinity. When r is equal to 0, the potential energy is 0. While near the Earth, we have the convention where the 0 potential energy is when you're on the ground, where z is equal to 0. 7, Hooke's law. Hooke's law is a spring. Force is minus kx for an ideal spring. If you stretch it, say a certain x away from like the equilibrium, then the force is going to be back and proportional to the distance. So if you were to pull it to the right, say this is positive x, then the force is to the left. So we just do the same game. I'm going to go from x to 0 to the center and see what speed we pick up. Then this would be from x to 0. This is a plus, the minus sign. The minus sign comes in when you replace the f with the minus kx. So the minus kx here. And see, notice that you can flip this around and go from 0 to x kx. This is personal choice, you know, what you want to do, because you might just say, let's just pull the thing back and let go. If I pull the thing back, I'll do this work, 1/2 kx squared, because when I integrate this, this is going to be k, you know, x squared over 2 from 0 to x, going to get this. So that's the work I would do to pull it to the right. And then if I let go, that'll be converted to the 1/2 mv squared. You know, when it gets to the center, it's going to be moving at that speed. So the potential energy for the spring, potential energy for the spring, that is 1/2 k x squared. Just like if we did the mass, picked it up, we would have mgh here, pull it back, get 1/2 kx squared. Let's go use Newton's law with Hooke's law. F equals ma, and we plug in minus kx, and the acceleration would be minus k over m times x. And it's conventional to take this constant, omega naught squared, to be k over m, and you'll see why in a second. So omega naught is the square root of k over m. Then you have a is minus omega naught squared x, and this is basically saying the second derivative of x with respect to time gets you back the same function x with some constant in front, and we know that cosines and sines do that. When you take the derivative twice, you get the same thing back with the constant. So if you take, say, x to be a cosine omega naught t plus b sine omega naught t, when you take the derivative of this thing, so you'll get a, and you'll get minus the sine omega naught t, and then you'll get an omega naught, you know, popping out of there. Then if you take the derivative again, you'll still have the a, still have the minus sign, because this will get you a cosine. And then when you pop out the omega the second time, you get the same thing, see, back with the omega naught squared. And the same thing will happen with this. You get the cosine with the omega, and then negative the sine. So this will get you minus b sine omega naught t omega naught squared. So the solution to the Hooke's law problem is the sines and cosines. So if I say this is the middle, and this represents oscillations, where this is x to the right, so your force is back, minus kx, the solution would be sines and cosines, and your initial conditions would depend on what A and B are. So that's a neat application showing Newton's second law and Hooke's law. Okay, let's go intro 8, Pascal. And first one we'll do is Pascal's law. Pascal's law is a cool law where you are, well, there he is. Pascal's law is a cool law where, let's look at here water, and let's take a block of water. So here's a block of water underneath water somewhere. Say it's a height h. Okay, let's take this block of water to be, this is like the surface of the water, and this would be like down below a distance h. And this is an area. And mg is the mass of the water, and then g is your weight. So your force is equal to mg. Remember we talked about that before. That's due to ma, because, you know, force is equal to ma, which is mg when you're looking at gravity. And here, if you're on the ground at rest, that's your weight. And your pressure, capital P, is going to be your force per area. And that's the pressure down here at the bottom. So the pressure is the force per area, and that's equal to mg over A. And here the mass is your density times your volume. All right, so that's the density. This is density. Like how many kilograms per cubic meter. So this will be then, here your volume, by the way, is your height times your area. So this is your area times your height, G, divided by the area. Areas cancel, and you get rho GH. You get this cool rule. That's Pascal's law. It basically says if you go down a certain amount of the water, you get more pressure. And here, what's really neat about this is that if you go down here 10 meters, which is about, you know, like 30 feet, then turns out you pick up another atmosphere. Now, atmospheric pressure, P naught, is 14.7 pounds per square inch, also called 1 atmosphere, also called 1.013 times 10 to the 5th PA, named after Pascal. So these are like Pascals. So the pressure underwater, you might say, is, well, you have the pressure at the top first, and then you have the rho GH. So this means if H here is 0, like you're measuring this from above, you're going, this is your depth. So if you're at the surface, then just set atmosphere. And then if you go down, for every 10, you go down. And I can show you that's kind of cool. If you have here 10 meters, since G is roughly 10, it's like 9.8. So it's Newton per kilogram. Remember, we showed that this could also be Newton per kilogram. And for water, this is 1,000 kilograms per cubic meter. And that's cool, because look at that. You get 10 to the 5th. 10 to the 5th Newton per meter squared, and that's named in Pascal's honor as a Pascal. So it's 10 to the 5th Pascals, equal to 1 atmosphere. That's cool. So you may use that somewhere in our course. Then 2 is the Pascal Triangle. And for a Pascal triangle, basically what he's doing is, the triangle is very easy to make. You just put 1, like here 1, then you add these 2 numbers together, and then here you add these 2, and here 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And that gives you a plus b to the nth power. That gives you the coefficients. Like if you have a to the n plus then A, let's say here, to the n minus 1, and B, like what do you put here? Like what's the coefficient? And then when you have n minus 2 and b squared, like what do you put there? See. So here, if you work the a plus b to the 0th power is 1, so that's that top one. And then if you have a plus b to the 1st power, you get a plus b. So the coefficients are 1, 1. Then if you have a plus b squared, you get a squared plus 2ab plus b squared. And that's this next one, 1, 2, 1. And you may recognize that's coming from the cube. So this is very, very nice to know. And you can have fun thinking about it, like how many ways can you pick all the fruit to be apples? You have apples and bananas, and I'm going to have n choices. For all these, I'm going to have n things. Here's though all of them are apples. Well, there's only one way. That's why all these ones are there. Then how many ways to pick one banana? Well, n. Since you got to pick n pieces of fruit, there's n different ways. So this coefficient here is going to be n. See? And then how many to pick 2 bananas? Well, n ways to pick the first one, n minus 1 to pick the second one, and then divide by 2 because it doesn't matter what order we're in. And that's going to get you the next term. So I just like to review that for you. It's very, very neat. And the formula I like to remember, the general case is very, very easy to think about, because what you basically do when you do this a plus b to the n, if you put here, say, you start out with the 1, then the next one is n. You can think of this as n over 1. Then the next one is n minus 2 over 1 times 2. And that's a to the n minus 2 and b to the squared. And the next one is n minus 2, n minus 3 over 1 plus 2, over 1 times 2 times 3. And so on. Isn't that a cool way to remember it? And you might remember from a class that there's a convention that you can find here the general case where you have, these are the cases, n is 0, n is 1, n is 2, n is 3. And then if you go in, that's your r, like 0, 1, 2. Then n r is n factorial over r factorial, n minus r factorial. Let's go ahead and do one. Say you want to do n is 4. 0, 1, 2, 3, 4. That's over here. And you want to do r is 2. 0, 1, 2. So that would mean n is 4, r is 2. This is 4 factorial over 2 factorial, and 4 minus 2, another 2 factorial. This is 4 times 3 times 2 times 1 over 2 times 2. This cancels, and you get 2 times 3, you get 6. That's it. So that's kind of neat. I'm pretty sure you saw that before. This is a quick little review of the Pascal Triangle. Pascal, a very famous guy. Look at this. This is physics. He's known for physics. This is mathematics. He's known for mathematics. And he's known for philosophy. Very powerful philosopher. And Pascal's wager, philosophy in terms of probabilities, where he wrote a treatise talking about should you believe in a creator in terms of probabilities. And it's very interesting. Team taught humanities at UNCA for many years, where Darrell Howard, my leader of that group, which is team taught by 16 faculty, a philosopher, he actually used some of Pascal's writings in the humanities course. That's how I encountered the wager. Okay, now we go to 9, and 9 is the method of undetermined multipliers. You're probably familiar with the formula where you figure out like the best area if you have, say, a constant length for perimeter. So you have like 2x and 2y, and like that's your fence. And you could like maybe do more like this, or like something else. You want to find the maximum area. So the area is equal to x times y. And what you do is you do a max spin problem. You basically get rid of like the y using this formula and take a derivative, set equals 0. And when you do that, you get the famous result that x has to equal y, and that's the perimeter divided by 4. So you have a square. That a square is like the biggest area. But if you take a dA and use partials, partial a with respect to x, say dx, plus partial of a with respect to y, dy, you would want to set that equal to 0, but the problem is you got to get rid of that dy. That dy and dx are related. They interact. So if you change the dx, you can change dy. So when you set this equal to 0, which is what is going to happen, you can't set these individually to 0. So you had to get rid of that y in here and just have a function of x. And then you took df dx equal to 0. So in other words, df equal to 0 works. But there is a really cool trick that you can use to make this work. What you do is, to be able to set these to 0 independently, what you do is this: dA minus some lambda dl. Now you can't change the perimeter. So the perimeter is constrained. You can't change the perimeter. So dl is going to be equal to 0. And dA is going to be equal to 0 when you do this minimum situation. But now if you do this, you have the derivative of a with respect to x minus lambda, the derivative of L with respect to x dx, plus the derivative partial of a with respect to y minus lambda L with respect to y equal to 0. And now what we do is we're going to pick at lambda. We're going to pick lambda so that we can say that these two, there's a dy here, that this dy and dx and dy can be independent, because the lambda is going to help us do that. So now we can set what's in front equal to 0, as if these were independent. So when we do that, and we get these equations, then here you have a is xy and L is 2x plus 2y. So the partial of a with respect to x is going to be equal to y, and the partial of L with respect to x is equal to 2. So using this formula, you have y minus the lambda times the 2 equals 0, which means y is 2 lambda. And you do the same thing for the x, you get x is 2 lambda, which means x and y are equal, and you got yourself your square. So that's a cool trick I'd like you to know about, which we will use later in our course. And the last thing, 10, is the ideal gas law. And the ideal gas law is the pressure times the volume is number of moles times a constant times T. And I have this reviewed nicely here for you in the book. Bodes Law, that if you keep the temperature constant, pressure and volume inversely related. Charles's law, at constant pressure, V goes with T. And then Gay-Lussac, at constant volume, P goes with T. So here they are: constant T, inversely proportional, Boyle's. If you have constant pressure, then V goes with T. If you have constant volume, P goes with T. But this is the summary of the law. And physicists go by the number of particles, then they have a different constant. And they use, this is the number of particles, and this one here, number of moles. And the way the moles work is if you have Avogadro's number of particles, 6.022 times 10 to the 23rd, you have a mole. So the number of moles is the number of particles you have divided by the Avogadro's number. Okay.